So to locate inflection points, find intervals where your second derivative is greater than 0 and the intervals where the second derivative is smaller than 0. So where it's positive and where it's negative. The point where that second derivative changes sign is the point of inflection. So the point where it goes from concave down to concave up is the point of inflection. And they don't always look like that. They have quite a few different looks. So let's find the intervals of increase or decrease for this example. First thing we need to do, find that derivative. Next, solve that derivative for when it's equal to 0 and when it doesn't exist, and then do the sign test. All right, you ready? Let's do it. So C prime of x. I'm going to have to use the product rule. So I'm going to have the first times the derivative of the second plus the second times the derivative of the first. All right, so let's go ahead and simplify this. So I've got x to the 1/3, and then I have x plus 4 on the top, and 3x to the 2/3 on the bottom. All right, well, remember I need to combine them because right now my goal is to have it as a fraction. Okay, right now it's something plus a fraction. I want a fraction so I can set it equal to 0. So I can find out where the fraction equals 0, and then also where it doesn't exist. Okay. So I'm going to multiply the first one by 3x to the 2/3 so I can get this as my LCD. So I'm going to have 3x. This one here combines to give me 3x. And then this numerator just goes along for the ride. And then now everybody is on top of this denominator of 3x to the 2/3. Simplify that just slightly, combine like terms. And this is my derivative, completely simplified. All right, so that's my first thing. Oh, here, wait just a second. Technology. My writing disappeared on the top and I don't know why. Okay, anyways, as I was saying, now we're going to take this derivative and we're going to set it equal to 0. So we're going to solve that. So I'm going to have 4x plus 4 all over 3x to the power of 2/3 equals 0. So remember, because it's a fraction, in order to solve this being equal to 0, I'm just going to take the numerator and set that equal to 0. So 4x plus 4 equals 0. Subtract the 4 from both sides and divide by 4. And I'm going to end up with x equals -1. All right, there's one of my critical numbers. Next, I need to find out where the derivative does not exist. And since this is a fraction, I'm just going to take the numerator or the denominator and set that equal to 0. And if I divide by 3 and take everything to the 3/2 power, I basically discover that x equals 0 is my other critical number. All right, let's do a sign test. So I can, again, look at every single piece of that derivative and plug the values in, or just look at the derivative. These are a little long. I'm going to run out of room. All right, my first critical number is -1, and the next one is 0. So I'm going to pick a test point, something that's smaller than -1. So I'm going to pick x equals -2. And maybe now I wrote it too small. X equals -2, that's my test point. And then between -1 and 0 is -1/2. So I'm going to plug in -1/2. And then greater than 0, I'm going to plug in 1. All right, if I plug those things into 4x plus 4, I'm going to end up with a negative, a positive, and a positive. If I plug in those values into 3 times x to the 2/3, I'm going to get a positive, and a positive. If I plug them into the derivative, I'm going to end up with a negative and a positive and a positive. So if I look at that cumulative effect on the derivative here, I'm going to have decreasing here because it's negative, increasing here because it's positive, and increasing here. So it changes from increasing to decreasing, from decreasing to increasing at x equals -1. All right, so let's draw some conclusions. Okay, so here are my critical numbers, -1 and 0. And until I get to -1, I am decreasing. So I am decreasing on the interval as x goes from -infinity to -1. And then I am increasing on these two intervals. All right, now I can't just stick them together. This is a two-piecer. So it is increasing from -1 to 0, and then from 0 to infinity. And notice that x equals 0, this is where I have a vertical tangent. So that's where the 0 is going to be an issue. And let's take a look at the original function, take a look at a graph of it, and see if it's increasing at that 0. Because the 0 I've got that does not exist for the derivative, but the 0 isn't a problem in the original function. So I'm going to graph this function. I don't really have room, but I'm going to do it anyways. X to the power of 1/3. Sorry, I'm typing it into my calculator. And x plus 4. I'm going to graph it. Let's see what it looks like. Ah, interesting. So it kind of looks like this. Okay, and I would say it's increasing here at 0, so that's going to be okay. So we don't have to write our interval as 2 pieces. We'll write it in 1 piece as it goes from 1 to infinity. All right, always use a graph to verify, always, always. Let's look at the next part of this example. Now, the next part, they want us to find the local minimum and maximum values. So we're going to look for sign changes. And that's from the previous page. And not for f of x, but for c prime of x. And that happens at x equals -1. And specifically, it's a minimum because it was decreasing and then increasing after. So I've got a local min at the point -1, -3 if I plug this into the original function. Okay, or if I just want the x coordinate. Next, let's find the intervals of concavity and the inflection points for this function. So what we're going to do is we're going to take the second derivative, and I'm going to write the first derivative up here so I got some room. And poof, look at this. We've got a second derivative. So I didn't realize it had stopped recording for a second, but I'll explain it. So here I'm going to use the quotient rule. Here's my low times the derivative of the high minus my high times the derivative of the low, all divided by the low squared. All right. Next, I'm going to simplify here. When I'm simplifying, basically, my goal is to get rid of this denominator here. I could build up denominators like I did in the last problem. That works too. But because this is a fraction where I've got a fraction within a fraction, if I just multiply top and bottom by the x to the 1/3, that'll get some things to cancel. So when I multiply that out, end up with the x to the 1/3 times 12. X to the 2/3 gives me 12x. When I multiply this here, the denominator cancels, and I'm just left with the 8x plus 8. Now, don't forget about that minus sign. That minus sign takes a turn with both 8s. So I'm going to have a minus 8x minus 8. 4x, yep. Minus 8 all over 9 divided by x to the 5/3. So simplified, I got it. Now I need to do the same thing I did before. I need to find out where this second derivative is equal to 0 and where this second derivative, does not exist. Okay, so it's equal to 0 when the numerator of this fraction is equal to 0. So I need to add 8 to both sides, divide by 4, and I'm going to get 2. So here's my first critical number. And it does not exist when the denominator is equal to 0, and that's going to happen when x is equal to 0. So I'm going to do a sine test. So here I've got a space issue. I'm kind of out of space. Let's see. Let's go ahead and do my table right here. All right. My first one is at 0. My first critical number is at 0. And my next critical number is at 2. I'm going to use test points here. So something smaller than 0, -1. Something between 0 and 2, 1. And something larger than 2, I'm going to use 3. I'm going to plug those values in there. So if I just plug those test values into the second derivative, I'll see I get a positive, minus, and minus. If I plug it into the 4x minus 8, I see I'm going to get a negative, negative, positive. And if I plug it into the 9x to the 5/3, I'm going to get negative, positive, positive. And kind of notice, you know, if I multiply negative by negative, I get positive. Negative by positive, I get negative. Okay, and positive, positive, I get, oh wait, positive. Oh, sorry. Yet another typo. All right. Good thing I looked at that. Okay, so let's look. So this is positive. This means it's going to be concave up. This is negative. It's going to be concave down. This is positive. It's going to be concave up. All right, so let's write some answers in here. So I've got concave up on the interval from negative infinity to negative 1, and then from 2 to infinity. And then I'm concave down in that middle interval from 0 to 2. And then I've got inflection points in these locations because that's where it changes signs. So I'm going to write that over. I'll put here's this answer here. I'm going to put this other answer up here because I'm out of room and I'm on PowerPoint. Ugh. Thanks, COVID. All right, so I'm going to have inflection points at 0, and then I need to find out that output value, and 2. And then don't forget, I'm plugging these values into the original function. So I get 0, 0, and 2, and 6, and the cube root of 2. I'm going to plug those in. So those are my inflection points. All right. These are long and fraught with potential issues. So just take your time as you're working through them. And always, always double check your stuff with a graph. All right, so let's look at the second derivative test. Don't be fooled by the name. The second derivative test, well, I guess it's kind of well named, but you use it to find increasing or decreasing or max or min stuff, okay? So you use for max, min, okay? Specifically, like if you have a maximum at a critical number, notice that a maximum is on a curve that's going to be concave down, and a minimum is going to be on a curve that's concave up. So we can use that for the second derivative test to give us some information. Okay, so let's let C be the critical number of a function f, all right? And this critical number is found by finding the critical numbers of the first derivative only. Next, let's suppose that f prime and f double prime exist on the interval I containing C. In other words, we can find both of those derivatives, and those derivatives exist. If the second derivative is positive, then f has a local minimum at C. So if it's a concave up, I've got a minimum. If the second derivative is negative, then f has a local maximum at C. As we were saying before, if it's concave down, it's going to be a maximum. But if f prime of C equals 0, then the second derivative test fails, and you must try the first derivative test to figure out if it's a maximum or a minimum. All right? So, because keep in mind, if you have a leveling off point, right? If you have a leveling off point, you'll have a horizontal tangent there, but it's not a max or a min. Okie dokie. Let's do the second derivative test. So we're going to use calculus to analyze the curve y equals x to the 4 minus 4x cubed with respect to local extrema, concavity, and points of inflection. We're then going to use this information to sketch the curve. Okay, so let's do that. Find y prime first. 4x cubed minus 12x squared. I want to find where y prime is equal to 0. And it exists everywhere, so I don't have to worry about that part. So 4x cubed minus 12x squared equals 0. I'm going to factor out a 4x squared. I'm going to end up with x minus 12. And then x equals 0 and x equals 12 are going to be my critical numbers of y prime. So I'm just going to kind of circle that. All right. Now, they want us to do a bunch of stuff. They want us to figure out the local extrema, the concavity, and the points of inflection. So let's go ahead and find our second derivative now. All right, our second derivative is going to give us 12x squared and then minus 24x. And now what I'm going to do actually is I'm going to find my extrema first. Okay, and I'm going to use this second derivative test. So I'm going to find the extrema first right here. So I'm going to take my critical numbers and I'm going to plug those into y double prime. So I'm going to evaluate at 0. So if I plug y double prime in, I've got 12 times 0 squared minus 24 times 0. This gives me 0. Aww. Second derivative test isn't telling me bupkis. All right, I'm going to have to use the first derivative test. For y double prime, if I plug in 12, so I get 12 times 12 squared, so 12 cubed minus 24 times 12. It's definitely going to be a positive number. I don't know what though. Let's plug it in and find out. I'm going to get a whopping 1440. Now, I actually don't care about the number, but I care about the fact that it's positive. So that means at 12, it's concave up. So I know that I've got a local min at 12. All right, now to continue my extrema, so this right here, this was my I used a second derivative test, so I found a local min at x equals 12. But I couldn't tell anything about 0. So I'm going to have to look at that, but I'm going to have to do a sine test with y prime. So let's take a peek at that. So just kind of, I already know what's going on with 12, so I'm just going to do, I've got x equals 0, and I'm going to look at something smaller than 0 and larger than 0. That's not a critical number. And I'm going to plug that into the first derivative. So if I plug -1 into the first derivative, I'm going to end up with 4 minus 12, and that's going to give me a negative number. So that means it's decreasing. So when I plug in 2 into my original function, I'm going to have 4, sorry, not original, my y prime, 4 times 2 cubed minus 12 times 2 squared. That's going to give me a negative 16. So I can see that this is going to be a leveling off point, right? I'm going to have a leveling off point. It'll look like this at x equals 0. So no extrema. All right. Let's take a look at concavity. So in order to find concavity and points of inflection, I am going to have to find the critical numbers of y double prime. Okay, so for concavity and points of inflections, I'm going to find the critical numbers of y double prime. So I'm going to set it equal to 0 because it's a polynomial and I don't have to worry about where it doesn't exist. So I'm going to have 12x squared minus 24x equals 0. Remember, this is a polynomial, so we're going to solve it by factoring. And I'm going to have 12x that I can take out. And I'm going to end up with x equals 0 as a solution and x equals 2 as a solution. Well, they're already nice and neat and written in order, so let's create a sine table out of that. So something smaller than 0, I'm going to use -1. Something between 0 and 2, I'm going to use 1. And something larger than 2, I'm going to use 3. So when I plug that in there, if I plug -1 into y prime, I'm going to get 12 times +1 and then plus 24. So this is going to be a positive. So this is going to be concave up in this interval. If I plug 1 in here, I'm going to have 12 minus 24. That's going to be negative. So this is going to be concave down, and because I have a sign change, I know that x equals 0 is going to be an inflection point. And if I plug in a number larger than 2, we chose 3. If I plug 3 in there, I'm going to have 12 times 3 squared minus 24 times 3. And that's going to give me a positive number. And that means it's concave up. So that means I also have an inflection point at x equals 2. All right, so let's write those conclusions. So I've got concave up on the interval. So we were up here. So all the numbers smaller than 0. So -infinity to 0. And then the last one here, all the numbers larger than 2. So from 2 to infinity. And it's concave down in that middle interval between 0 and 2. So there's that answer. And then I know that I've got inflection points at x equals 0 and x equals 2. And if I plug those into the original function, it's going to give me the point 0, 0. And if I plug in 2 to the original function, so 2 to the power of 4 minus 4 times 2 to the power of 3, well, that's going to give me a -16. Okay. So we're then going to use this information to sketch the curve. I'm just going to kind of do a visual tour. So first of all, we can see from our first derivative here that our function starts off like this. It's going to be decreasing, decreasing, and then leveling off at x equals 0, and then going down. And we can actually see that there's an inflection point there too. We can see at that leveling off it does that. Next, we've got a local minimum at x equals 12. So somewhere it's going to go from concave up to concave down. It's going to change. Then I'm going to have a minimum. Oops, I can't go right lower below that. I'm going to have a minimum at 12. And then it's going to go up and up and up forever, amen. So essentially, this thing is going to look like this. But we should verify that with a graph. And yep, if we graph it using a graphing utility, we see that all of our hard work has told us the truth. Okay, a couple of things. The second derivative test is actually really nice, but you just have to remember some things about it. First of all, the big pro is that there's less work with interval testing, okay? You find the first derivative, okay? So you just basically find the first derivative and then find your critical numbers of your first derivative. And then you find your second derivative, and then you take those critical numbers and you plug the y prime critical numbers into y double prime. So it's a little bit faster than having to do all those test points. There are some cons though. First of all, the second derivative can be hard to find, right? It can be. It can be hard to find. It can be hard to simplify. Just depends on the first derivative, what that looks like. And then this is the big one here. This is the big one here, because students forget this all the time. If the second derivative equals 0 for that critical number, then the test fails. And students often forget that. They say, oh, okay, it equals 0. You know, they forget that 0 isn't positive or negative, and then they just make a judgment claim. And you want to be careful of that. So this is something I find that students kind of like. So bear with me. I'm just going to be explaining a lot without being able to be in front of you and moving my hands around. So visualize me standing in front of you, moving my hands as I say these things. All right, first derivative test and second derivative test. Okay, so these are used to determine increasing and decreasing only. So I should say the first derivative test is used for increasing and decreasing, and the second derivative test tells us the concavity at the critical numbers, which we can use to find minimums and maximums.
What's up? Hi, Lucy.
Hi, Pumpkin. Here, I just have to finish recording this video. Pixie, don't bark anymore. I love your pants.
Thanks.
Yeah. All right, I'm almost done. Okay, the thing to remember with the first derivative test is that you are finding f prime of x. And then for the second derivative test, you are finding both f prime of x and f prime, double prime of x. So first of all, just remember that when you're finding your critical numbers c, these are always the critical numbers of the first derivative. For the first derivative test, you perform a sine test on the first derivative. You plug in test values, not your critical values, into your first derivative, and make sure that you're always using test values that are larger or smaller than your critical numbers. If your answer is positive, then f of x is increasing. If your sine test is negative, then your original function is decreasing. When you're performing a sine test on f double prime of x, you do not need to find critical numbers again. You take the actual critical values, the c values, and you plug them into the second derivative. Remember, if it equals 0, it fails. You got to go back to the first derivative test. But if you plug it in and it's positive, then you know that there is a minimum at that critical number. And if you plug it in and it's negative, then there's a maximum at that critical number. And of course, don't forget, always, always, always check it with a graph, right? Why do all that work and submit something wrong? It'd be a huge bummer.